In the last lecture, we looked at various examples of non-gray surfaces which have an impact on calculation of radiative transfer, and we saw how the analysis for an enclosure with non-gray surfaces has to be done iteratively. We have to, if the temperature of a given surface is not known, you have to guess the temperature, calculate the radiative transfer at one wavelength, integrate over all wavelength, and then obtain the total heat transfer. If that does not agree with the specified heat transfer, then you go through iterative procedure. Now, to give an example of a real world problem, here is an example of heat transfer between two parallel plates of tungsten. Tungsten plate, two plates are there, and you want to know what the heat transfer is. Tungsten is a metal. So, we all know by now that the hemispherical spectral emissivity of tungsten is a function of wavelength, as it is given here. It is high at low wavelength in the visible around 0.4, 0.5 value, and then it comes down rapidly and goes to around 0.05 at high wavelength. Now, suppose the two plates on either side are metal. What is the heat transfer rate? So, you have to calculate this numerically by calculating flux at certain wavelength interval and average over all the wavelength. I have given you just a result obtained from this NASA paper. Now, what we have done here is we have shown the ratio of gray to non-gray. So, let me explain that through this example here. So, if it is gray, you know that heat transfer from plate 1 to plate 2 will be sigma T1 to the power of 4 minus T2 to the power of 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. If it is non-gray, the same calculation will be done as follows: integral over all wavelength 0 to infinity, black body emissive power of the two surfaces divided by the spectral emissivity into d lambda. Now, you must realize that this problem is similar to the Dewar flux problem, except that in the case of Dewar flux problem, we assume that emissivities are so low that these two terms are large compared to this term. We neglected this term, and that made the integration easier. Here, we cannot do that, emissivity is not that small. We retain this term. We retain this term, this integration has to be done numerically. You cannot do that analytically. So, this has been done numerically in that NASA report. Now, what we are doing is this is gray, this is non-gray. So, taking a ratio of non-gray to gray. So, the idea of this plot is to give you an idea of what is the error that occurs on account of an approximation made in the problem. Suppose you assume a non-gray surface to be gray, you would like to know how much error is involved. Now, this is of great practical relevance for engineers, because if it is a gray surface, you can do this calculation by hand, because that is a very simple result. If it is non-gray, you will need a computer to do this calculation. So, if you are in the field and you want a quick estimate and you assume a gray surface approximation, you would like to know what kind of penalty is involved in that approximation. So, we will go back to that graph and look at this. So, this is Q non-gray to gray ratio, sorry gray to non-gray here. So, you can see that all the numbers are below 1 here. So, what it means is that if you make an estimate of radiative heat transfer between two tungsten plates, assuming them to be gray, then you will overestimate the heat transfer compared to non-gray, because non-gray is in the denominator. And so, that is the point, that is here. So what we want to do now is to look at the result. Notice that the x axis is the temperature difference between plate 1 and plate 2. So, if the temperature difference is less than 1600 degrees Kelvin, then the ratio of gray to non gray is approximately constant. This is a useful result to have, which means I can make a rough calculation of the heat transfer assuming to be gray and multiply by a correction factor here, because if you assume it is gray, you will overestimate. You can multiply by a factor like 0.95 to get the correct answer. So, between temperature difference of 0 to around 1600 or 1000, I would say, you can see that the ratio is almost a constant. So, that is useful information for an engineer, that you can use gray surface approximation and have a correction factor and you can manage. But notice that as the temperature becomes larger than 2000 degrees Kelvin, there is a large error here which is changing with delta T, and you can see that errors of the order of 30% is possible when delta T is around 3000 degrees Kelvin. And therefore, when the temperature difference in the two plates is very large, then one should be very careful about a gray surface approximation. So, this is a good useful information we get from this report, that gray surface approximation is good if the temperature difference in the two plates is not large, less than 1000 degrees Kelvin, but as you go to higher and higher temperature difference, the gray surface approximation becomes worse and worse. This is not surprising, because imagine the lower plate was at 4000, upper plate was at, let us say, surface 1 was at 1200, surface 2 was at 4000. Then the peak of the emission from the surface at 1000 will be around 3 micron, while that of the other surface will be around 1 micron. So, the portion of the emissivity curve, so one of them will sample this emissivity, the high temperature surface, because it is having their peak radiation more like around 1 micron, while the other one will sample this region where the emissivity is lower. There is a huge difference in emissivity between this region and this region. While when the temperature difference is small, the emission wavelengths are all comparable. So, you do not make very large error in the estimate of emissivity. So, we get a very good information from this work, which is that the assumption of a gray surface in a given situation is sustainable if the temperature difference between the different surfaces are not very large. But if the temperature difference is very large, then a gray surface approximation can lead to errors of the order of 30 or 40%. Now, whether that error is acceptable or not depends on the given situation. I would argue that in the case of certain application, it may not be acceptable 30% error, but there are situations where one has great difficulty in getting actual properties of a surface accurately. Then the error in emissivity calculated itself can be 30%. If the surface property is not known accurately, then if it itself has an error of 30%, then you may not mind a 30% error in due to gray surface approximation. So, whether you make a gray surface approximation or not depends on the accuracy demand in a given situation, and that can vary a lot in a real world situation in engineering. Certain field conditions, one would not mind 30-40% error if one wants a rough estimate of what is the heat flux. On the other hand, if you are going to design a furnace and cooling system, then you need a fairly accurate estimate of the heat flux, maybe within 5%, so that you can design your cooling system precisely. But at least we got an idea of the range of errors that can occur, which is anywhere between 0 to 30%. Okay. So, that completes our discussion on enclosures with diffuse isotropic reflectors and emitters and gray and non-gray surfaces. Now, there are some situations that we encounter, especially application to solar energy use, wherein the surface you have is not a diffuse isotropic emitter or reflector. Very often there are surfaces which are reflecting like a mirror. Okay. Such surfaces are called specular. Here is a picture showing the difference between mirror like reflection shown here and diffuse reflection which is shown here. So, this is the kind of reflection you will see if the surface is highly polished and free of any defects, and this is what you will see in a rough surface where the reflection will be in all directions. Now, the analysis we have done so far of enclosures is for surfaces of this kind, diffuse isotropic reflection and emission. But there are occasions where you encounter surfaces which are reflecting like a mirror called specular reflector, and the question is how do we change our analysis to situations where the surfaces reflect like a mirror, that is specular reflection. Now, this problem gets more difficult compared to this problem, because when a surface reflects diffusely, that is equally in all direction, then the memory of where the photon came from is lost, because once the photon strikes the surface, it is reflecting equally in all direction. So, we do not really care where it came from. So, that is why our analysis was based on the concept of radiosity, which merely added the reflected radiation with the emitted radiation. Both were equal in all direction, there was no directional preference. So, our analysis was mainly based on a concept of radiosity, which added the reflected and the emitted radiation. But suppose you have a surface which reflects it this way, but emits like this, then clearly the reflection term must be tackled in a different way than the emission term. In the reflection term, you must worry about where the radiation came from, because it came from somewhere here, it will reflect this direction. If it came from somewhere here, it will reflect in this direction. So, where the photon goes after reflection depends upon where the photon came from. So, the memory of the system is retained. So, this makes the problem complicated. Now, when a surface reflects like a mirror, it is very important to know where the photon came from. So, you have to trace the photon's history through the enclosure. So, this is called ray tracing, and this methodology is now getting more and more popular, but you can imagine that it is quite laborious and tedious. You have to look at each photon and trace its path through the enclosure as it is reflected in a specular fashion in a given situation. So, let me give an example of that. So, suppose your enclosure like this and radiation came like this, you have to follow the radiation reflected like this, like that, like this, like this. So, you have to follow the ray through all these reflections. So, you can do it today with a computer. So, this method of tracing the ray and following the photon till it is absorbed. So, you start with the photon emitted by some surface and follow that photon through after multiple reflections until it is absorbed. Okay. And you do this same procedure for maybe 1,000,000 photons. So, you can imagine it will take a lot of time, but today with the availability of high speed computers and a huge memory that we now are able to get, you can do it. So, this is now standard procedure, and there are software available which will do the Monte Carlo simulation for you very easily. But there is nothing to teach there, you just take the software and run it and it will give you the answer. So, we will not spend too much time in this course talking about Monte Carlo, but Monte Carlo is a very popular method because it can deal with any complexity. You can do Monte Carlo simulation for non-gray enclosure with many specular reflecting surfaces with complex geometry. Suppose geometry is very complicated, then also you can do, as long as you know the geometry and you can do the ray tracing. Okay. So, this method is getting more and more popular, although it is computationally intensive, still it is popular because it enables you to deal with very complex real world problems in which the reflection is not diffuse, the surface is not gray, and the geometry is very complicated. If all these three conditions are satisfied, it makes sense to go to Monte Carlo. But there are also other examples wherein the geometry is fairly simple, maybe only one or two surfaces are reflecting specularly, the rest are reflected diffusely. If that is the case, one can still extend the techniques we have developed for diffuse isotropic reflector emitter to an enclosure with a few surfaces which are specular. So, that is what we are going to now focus on. Now, let us now take some simple examples first to highlight the role of. Now, first example we take is, imagine two cylinders or two spheres. Okay. Now, I want you to mentally do the ray tracing. Suppose radiance emitted by the outer cylinder and it is reflected specularly in the outer cylinder. You can see, you can draw this graph, you can see that this ray will never reach 1 because it will be reflected only with this. The geometry of the problem demands that a ray which is some of the rays which are reflected by cylinder, the outer surface 1 will continue to be in this path only, while the other ray whose angle is smaller hits surface 1 will keep bouncing between surface 1 and 2. So, there are two kinds of rays, one ray which is reflected between 1 and 2 and never comes to 1, but other one which is after emission by 2 remains only in 2. So, let us keep that in mind, and so let us look at surface 2 and calculate. So, surface 2 emits this much radiation diffusely, the diffuse emitter, and it has two kinds of rays. The fraction which is reaching 1, the inner cylinder or inner sphere, reflects between 1 and 2, bounces back 1 and 2 till it is absorbed. The other fraction 1 minus F21 is only reflected between 2 and 2. So, let us go back to the picture to make sure that we understood it. So, sigma T1 to the power of 4 A2 F21 is this one, and sigma epsilon 2 sigma T to the power of 4 to 1 minus F21 is this one. So, the key point to remember is that these photons which do not hit 1 the first time will never hit 1 again, they will only be reflected with 2. So, that is what makes the analysis somewhat interesting. So, you only, in order to calculate the energy exchange between 2 and 1, you are only worried about this part. This part does not interest you, because it does not go between 2, it only goes between 2 and 2. Therefore, you can write Q 2 1 from 2 to 1 as the first ray which is hitting 2 and is absorbed by, from 2 hitting 1, absorbed by 1, assuming a gray surface here. So, alpha equals epsilon. Then if it is not absorbed, it will continue to be reflected between the two surfaces. So, it will undergo 2 reflections and again get absorbed, or 4 reflections and again get absorbed, and it is an infinite series. This is the ray tracing method which we had already adopted between 2 parallel plates. So, same logic, there is no difference. So, and similar logic can be worked for Q 1 2, energy emitted by 1 will only bounce back between 1 and 2, okay. And this can again be seen if you go back to that picture. So, energy emitted by 1, the tangent point will reach here and it will come back here, okay. It will never hit 2 again. So, the radiation that is emitted in this quadrant only will bounce back between 1 and 2, only radiation coming out in the other direction will go. And so, even from here this is the normal emission, this is the tangent, even tangent emission between from 1 will come back to 1, will not go to 2. Okay. So, once you have realized this, you can see clearly that you can write down the final expression for Q 2 1 as equal to, doing the infinite series summation, and A 2 F 2 1 is A 1 F 1 2 and F 1 2 is 1. So, equal to 1. So, this is divided by 1 minus so, similar result you can go for Q 1 2, it will allow the same thing, except that this will be sigma T 1 to the power of 4 A 1 and the net heat transfer difference between these two, and both involve A 1 now, interestingly. So, you take this quantity down, you remember that this 1 will cancel with this 1. So, you will be left with an interesting result which is a little surprising. So, Q 2 to 1 net is sigma T to the power of 4 minus T 1 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Okay. So, the surface is specular, then the final answer looks like that between parallel plates. So, when surface, outer surface here is specular, then the heat transfer between 2 cylinders or 2 spheres looks like heat transfer between 2 parallel plates. We had already used this idea when we looked at the Debye-Frost problem. We did not explain it as to why we use that formula. So, the formula that we used for, so that is to remind you the difference between this result and the result for this for specular surfaces, this is for DI surface, two cylinders. This is what we got earlier, DI surface, two cylinders, but if the two cylinders, the outer one is specular, then you get this. So, the main thing is that the outer cylinder A2, which is specular, only a portion A1 of that outer cylinder is actually interacting with the inner cylinder A1. The other part is not interacting. So, it looks like radiation heat transfer between parallel plates. The higher area of the outer cylinder is not actually seen by the inner area. So, this is a simple illustration of the role of spectral reflection on the radiation transfer between two cylinder, two spheres. So, profound impact, because for example, if you recall, we pointed out that between two cylinders, if they are both DI surfaces, as A2 goes to infinity, the outer cylinder becomes very large, then this term drops out. That is not true in the case of specular reflector. If the outer cylinder or sphere is a specular reflector, then the result is very different from if the outer cylinder was a diffuse reflector. If you have a large diffuse reflector, the second term drops out. If you have a large specular reflector, second term is, the outer cylinder is still important. Okay. Let me give an example. Imagine both cylinders surfaces have low emissivity 0.1 and 0.1, and the area ratio is 100. So, this 1 by 0.1 is 10 minus 1 9, and the ratio is 100. So, you will get 0.09, and here you get 10. Here you get 10 plus 10, 100 minus 9, 99, huge difference. So, this specular reflection case reduces heat transfer much more than the diffuse case, and that is the consequence of specular reflection. Okay. So, this result is worth remembering in a given application, wherein you want to reduce the heat transfer substantially between two surfaces and they are curved surfaces, then you are better off keeping the outer surface as a specular reflector in order to ensure there is more resistance to heat transfer from inner surface to outer surface. I must point out that we do not care whether the inner surface is specular or diffuse. That is totally irrelevant, because whichever radiation strikes the inner surface ultimately has to reach outer surface, whether the reflection is diffuse or reflection is mirror like, does not matter, because ultimately reaches surface, outer surface. So, the nature of the reflection in the inner surface is of no consequence to us. On the other hand, the outer surface, whether it is diffuse or specular, is very important. So, this is a point I want to highlight clearly before we go on to more complex situation. In this case, we are looking at a diffuse surface here 1 is below, and a mirror like surface 2 specular. Now, here what we are trying to appeal is to what is called the method of images. What he is saying is that radiation leaving 1 at two different angles reaches 2 and is reflected in a specular fashion to surface 1. So, although these rays are coming by specular reflection from surface 1. If you extrapolate these two rays, they seem to be coming from a diffuse emitter located exactly equidistant from this surface, like a mirror image. Okay. So, this mirror image of surface 1 seems to be the point from which these rays are emerging in a diffuse fashion. So, in the method of images, what we are doing really is exploiting the fact that if a ray is reflected from a specular surface, it can be imagined to be emitted from an imaginary surface equidistant away from this surface as this is. So, you create a mirror image of surface 1 with respect to surface 2 and pretend that a diffuse ray is emerging from surface 1 2, which is the image of 1 in 2 and reaching surface 1. Why we like this kind of construction is because if the rays are seem to be coming emerging from an imaginary surface which is diffuse reflector, then we can use the full power of the radiosity concept, because remember the radiosity concept is valid only for diffuse isotropic reflectors. Surface 2 is not a diffuse isotropic reflector, but you can imagine that the rays reflected from surface 2 are actually emerging from surface 1 bracket 2, and those rays emerging are diffuse and isotropic. So, to put this issue in a clearer fashion, so what we want to say is that radiation that goes from 1, remember 1 is a flat surface. Normally, if 1 is a flat surface, you will assume that F11 is 0. You cannot see itself, but you have now a mirror like surface 2 which reflects the surface 1 on the other side. So, what is happening is the rays are coming from surface 2 which seem to be coming from the image of surface 1 and 2. We want to incorporate. In addition to radiation leaving 1 and reaching 2 directly, radiation leaving 1 and reaching 2 can also reach 1 by other means, okay, and that is by specular reflection. Now, this I am going to now illustrate in a real situation where the problem is, I will take a rectangular enclosure okay, and you have surface 1, 2, 3. So, surface 1, 2 and 3 are diffuse isotropic emitters and reflectors, while 4 is a diffuse emitter, but a specular reflector. Okay. So, because 4 is a specular reflector like a mirror, you will get images of 1 in 4, we will call it 1 bracket 4, get an image of 2 in 4. So, I will call it 2 bracket 4 and you have image of 3 and 4. So, we construct these 3 imaginary surfaces 1 bracket 4, 2 bracket 4, 3 bracket 4, which are images of 1, 2 and 3 mirror images in the mirror 4. Now, for example, look at surface 2. Surface 2 is a flat surface, right. So, the diffuse isotropic surface will have no self peeking factor. So, F22 is 0, but the emission of 2 is reflected by 4 and comes back to 2. So, radiation from 2 comes back to 2 because surface 4 is a specular reflector. So, although the self peeking factor from the diffuse isotropic emission is not much, but a certain fraction of this emission is reflected by 4 will come back to 2 because 4 is a mirror. So, how much will come back? So, we will call that E22. Okay. E22 is the specular reflectivity of 4, how much is reflectivity times the shape factor from 2 bracket 4 to 2. So, this is a new thing we have to calculate and this enables 2 to see itself. So, surface 2 is able to see itself because of the specular reflection in surface 4. So, this is now a new shape factor for specular surfaces, which includes within it the specular reflectivity of the surface 4. So, I want to remind you that one of the advantages of shape factor definition, which is valid only for diffuse isotropic emitters and reflectors, was that it was a purely geometric factor. Once you knew the geometry of a problem, you can calculate Fij's once and for all and store it and use it many times. But when a surface reflects in a specular fashion like surface 4 here, then this factor E22, which can also be thought as a shape factor, but this depends on the reflectivity. This is not a purely geometric factor, it is depending on surface reflectivity. This slightly surprising result and you need to get used to this concept, because this concept is not like we had looked at earlier, it is a little more complicated. Similarly, let us look at surface 1. Radiation surface 1 can reach directly by diffuse emission, can also reach 1 by specular reflection. So, we will define E12 is equal to F12, but plus reflectivity of surface 4 times the image of 1 in 4 to 2. So, E12, the total radiation reaching 2 from 1 either by direct path or by the reflected path is defined as E12 equals F12 plus rho 4 specular times F1, 4 to 2. Again, notice that this is not anymore a purely geometric factor. It is also depends on surface properties of this surface 1. So, it depends on reflective of surface 4 and of course, geometry. So, this complicates our analysis somewhat. Previously, we could calculate shape factors Fij once and for all and use it in our radiosity method we discussed in the last few lectures. But once one of the surfaces is specular, the problem gets a lot more complicated. The new shape factor E12, which represents the amount of radiation leaving 1 reaching 2 either directly or through reflections. It will involve a term E12, F12 which is very geometric, plus rho f specular of surface 4 times F1 bracket 4 to 2. So, the new shape factor E12 is not a purely geometric factor. It depends on both geometry and the reflectivity of surface 4. So, this is a new concept different from what we had talked about so far. Now, what happens if the problem gets somewhat more complicated? So, let us now take this problem to a somewhat higher level to understand how the problem gets more and more complicated. So, now we have the same enclosure, one, 2, 3 and 4. Now, there are two surfaces which are specular reflectors. Okay. So, now we will draw images of 1 and 2 and 3 and 4. Let me draw it simple in a smaller way, so it is easy to draw the images. So, image of 1 and 3 is here, image of 3 and 2 is here, the image of 1 and I am sorry, I will rewrite this. Two and 4. Similarly, we have the image of 4 and 3, image of 2 and 3, and this is now a bit complicated, this part. It involves reflection in 4 and 3. So, it comes here, comes here, comes here. Or it now the radiation coming from 2 to 3 to 4 to 1. Okay. So, this gets a bit involved now, because there are two mirrors. Now, what is E12? So, E12 will involve the direct F12, then what comes from image of 1 in 4, what comes in image of 1 in 3, so I will make a light correction here. This should be, these images are 1 4 3 and 1 3 4. So, question is, what is E12 in this case? Radiation leaving 1 and reaching 2 directly or through specular emission in 3 and 4. First term is easy to understand, F12, but after one specular reflection, it can come from image of 1 in 4 to 2. So, the reflected radiation here seems to come from the image of 1 in 4 right behind here. Okay. Similarly, reflected emission from of 1 in 3 will give you this term. So, these two are the terms which are for one reflection. Now, you must remember there are multiple reflections involved here, because there are two mirrors. So, you have to account for multiple reflection terms, and that is done as follows. So, let me just rewrite what I wrote in the last slide. So, this is the first term, this is similar one for reflection surface 3. Okay. Now, come the multiplication terms, rho 4s, rho 4, rho 3s. And the image of 1, 4, 3 to 2. So, f1 4, 3 is the imaginary surface obtained after multiple reflections, that is which can be which is the one, this is multiple reflection, two of them are there. So, this includes this term and of course, one more term going the other way around. So, now we have four terms: the direct radiation, which follows the diffuse emission shift factor, the standard thing we use. Then we have after one reflection in 4, one reflection 3, then we have two reflection 4 and 3 and 3 and 4. And remember, once the surface reaches 2, that is the end of ray tracing, because surface 2 is a diffuse emitter. So, once it has reached surface 2, the story is over, because there is no further ray to trace, because 2 is a diffuse reflector. So, the memory is lost and we do not really have to keep track of the any images in 2, because 2 is anyway a diffuse reflector. So, this tells you how we are in a position to extend the concept of shape factor, which was derived for a diffuse isotropic enclosure, to enclosures containing one or two specular reflectors. And if you construct the images carefully and follow the ray tracing carefully and see how many images are there, and then you can write down the full expression by inspection. You can see this is quite a tedious method, but if you encounter such problems in the industry, you tend to write a specialized software to deal with that situation. In the present context, we are merely trying to teach a principle and an approach. We must recognize the fact that if there are more than two surface enclosures which are emitting like a mirror, then this methodology will get too complicated. You will not be able to track all the images. And another thing is, if the enclosure geometry is very complicated, it has curved surfaces like cylinders and some crooked surfaces, then this problem gets even more complicated. So, now practice is, if the number of surfaces which are specular is very large and the surface do not have simple geometry but complicated geometry, then this simple idea that we proposed here is not workable. You will go for Monte Carlo type ray tracing algorithms, which are now getting more and more prevalent, and the software is being developed. Now, just to complete our discussion here, assuming that such new shape factors are calculated, these new shape factors depend both on the Oort shape factor for diffuse surfaces, and all these terms involving specular reflection. So, this is not anymore a purely geometry factor, it is a geometry as well as the specular reflectivity of the surfaces. So, let us say we get all Aij's, how do we do the general problem? General problem has n surfaces, of which d are diffuse and n minus d are specular. So, divide the enclosure into two kinds, those which are diffuse reflectors, those which are specular reflectors, and you adopt for diffuse surfaces, this is J now, J between 1 and N, 1 and D, these are D diffuse surfaces, you can apply radiosity concept, no problem. So, you can define Q as radiosity minus irradiation, this is what we already covered. On the other hand, for the remaining n minus d specular surfaces, you have to treat the emission and reflect separately. You recognize the fact that radiation emitted by these surfaces is this much minus what is coming in is this much and absorbed is this much, and this is equal to Qj. This is in Watson meter square, remember this is per unit area. On the other hand, if the surfaces are specular, in addition to the emission term, you would account for the reflection terms. The reflection terms will have two components, what is arriving in a surface K will be what is diffuse emission So, you take J equals 1 to D, the D diffuse and calculate their radiosities, and after reciprocity that is what you will get. Okay. Plus for the surfaces which are not diffuse reflectors, you are going to consider E, which we just now developed. So, we will say emission from surface J and we will use EKJ. So, the radiation coming from diffuse isotope reflectors is treated differently from radiation coming from specular reflectors. In specular reflectors, you are looking at the emission from surface J differently from the reflection surface J, and you are carrying through all the reflected terms separately and putting them in EKJ. So, this approach would seem to be somewhat complicated, but it is not, except that you keep separate accounting for terms which come through reflection in the specular surfaces from those that come from diffuse reflectors. Once you adopt that, this problem gets to be fairly straightforward, and as I pointed out, the method we discussed here can only be applied for if you have a small number of surfaces. If you have a large number of surfaces, then this problem will get quite messy, and you may not be in a position to draw all the images and track all the cases. So, in such a case, you will go for Monte Carlo. So, if the situation, if the surface that you have are not flat and there are many spectral surfaces, then you cannot handle the spectral surfaces by method adopted here, it will get too complicated. So, you go for ray tracing and a Monte Carlo simulation in which every photon is separately accounted for. But for simple examples, the method suggested here will be useful. So, with this we pretty much come to close on our discussion on enclosures. We primarily covered diffuse isotropic emitter reflectors and gray surfaces primarily, and showed how radiosity method is very powerful. Then we showed how we can extend this to non-gray surfaces, and finally, we touched upon how we can tackle surfaces which are specular, but argued that you may have to use Monte Carlo if the problem gets too messy and elaborate if there are curved spectral surfaces.